Hello, we are going to talk about the basic operations with geometric figures, and we have our main four properties here, and most of these we're going to get done on. We're going to go over how these are true, and it may seem really self-evident but that these are true, but it's important that we understand why these work geometrically. So the first thing that we're going to go over is something called the triangular rule of vectors. So if you have vector AB plus BC, that's going to be equal to AC. And we can see that geometrically if I draw, let's say, a vector here, and we'll call that vector right there, and we'll call that A, B, and C. So we have vector AB, that's this guy, BC and this guy, and then if we connect the two right here, it's kind of messy. Let's see if I can get it a little bit better than that. It's a little better, right? So that vector right there would be AC. And usually how we represent these would be as such. So if I have, let's say, vector A, vector B, and then this right here, this vector would be A plus B, right? Vector A plus B. It's kind of the same up here, just a different notation. Now, we talked about in the other vector that a vector has both magnitude and direction, and if they have the same magnitude, same direction, they're equivalent. So if I draw its equivalent one right here, a little messy. Let's see if I can get this to be a little more neat. And if I go like that, then this equivalent vector is right here. So I have that vector, right? And then you can see that this vector right here is B, and this that's vector B, and this is vector C, right? And then you can see this proves the first property, the commutative property, right? I can see from this that AB plus BC, AB plus is equal to vector B plus C. So we can add those vectors together, and that's the commutative property. The associative property we'll do later. The next thing I want to talk about is just the zero vector, the additive identity property. Well, to quickly see what that's look like, imagine we have let's say a vector like this, and it's opposite direction. So it has the same magnitude but different direction, going the complete opposite direction right here. And if this is vector A, and then if we let this be equal to vector B, right? Well, I can, just like we've done in the other video, we know we could take this vector B and move it in any direction and it'd still be equivalent. And so if I take this vector B and move it to right here, going this direction, what happens? They end up getting to a point. So this is vector B, right? They end up going to ending up at a point 0, right? And when they're at a point 0, that means that what we know is that using the additive property, these added together, A plus B, right, is equal to B plus A, but it's got to end up to be 0. So we know that our vector B is equal to a negative vector A, and that's our opposite vector right here. So that's what this is equal to. So, and then this, you can see these properties can hold out pretty solid right now, since u plus our 0 vector is going to be additive property 0 plus u. You're going to get u. And then if we take our opposite, we're going to end up with the 0 vector. So that's what this is. Something else I want to go over real quick too is vector subtraction. So if I have, let's say, a vector going this way, and then a vector going this way, right? And then if I call this vector A and this vector B, right? And if I take its equivalent vector down here, or its opposite director down here, and move it in the opposite direction, I'll try to draw it nicely right here. This vector right here would actually be negative B, right? Right? I shouldn't draw it with this point right here. Yep. So let's go back to this. So if this is indeed and if this is the opposite direction, it's going in this direction now, right? And now we can see this vector going this way, right? That's that vector going that direction, this plus this. what is this equal to right here? This is vector A minus B, right? Good. But if I look at these ones right here, am I going to be able to copy this? Right here, and let's erase this out right here. But if I did it the opposite direction, if I did this the opposite direction, if I have A and B, right, but this time I move over this direction but go the opposite direction right here, right? And so I have this direction going here, but this time I'm going this. This guy right here is actually negative A, right? And then this wouldn't be going this direction, right? So I can get rid of that right there, here. And what do I have? This time this vector is going, this one went this way, and it's a minus vector B, right? Or better yet, but this time this vector going, this time this vector is going this direction, right? And this would be B minus A, right? Vector B minus A. So we see this a lot with vector subtraction. I want to point that out. So next thing we're going to go over is we're going to look at example 2, and it asks us to give you vectors in space, and it's AB plus CD and EF. Show geometrically what this works. So we have AB. Here's CD. It's equivalent vector, so you can see this goes over 3 and up 2. So 1, 2, 3, up 2. It goes to right there. And then this one here goes down 3 and over 1, 2, 3, 4. So from here I'm going to go 1, 2, 3, and then over 1, 2, 3, 4 to right there. So now we have that vector right there. And then, I did make a mistake, my bad. So I have to, this vector is over 3, up 1. So 1, 2, 3, it's only going to right there. Then this is down 3 and over, what did I say? 1, 2, 3, 4. So 1, 2, 3, 1, 2, 3, 4, right there. So now I have those vectors right there. And then now I can connect this vector right here. And that's the vector that we're looking to. And what I wanted to do is be able to use this to show. Right, so if you look at these, when you add these together, right, if I were to call this, well, if we use this one's U right here, and this one is V, and this is W, you could see if I draw this guy right here, right there, that is U plus V, right? That's U plus V. And then you can see this one right here would be, this way would be U plus V plus W, right? Good. But if I were to, let's see if I can erase this off real quick right here. Get right here, right? And then if you were to do it, if you were to look at this guy right here, this vector right here, that's V plus W, right? V plus W, right? And then you can see this is equal to U plus V plus W. And that shows the associative property right there. So we can use how that works. Good? So moving on, let's talk about scalar multiplication, right? So the first thing I want to talk about a scalar multiplication is we can use the our rule from before, the triangle rule. Let's say if I have a vector like this, and let's say it's split up into parts. Let's see if I can do a better job of. Let's see if I can split this up, right? Let's say it's split up into 4 parts right here, right? And we can call this, let's say, call that A, B, C, D, and E, right? And then we can see that vector AB, using the triangle rule, plus BC plus CD, right, plus DE, right, all is going to be equal to AE, right, the vector AE, right? Good. And then if these are all equal distances right here between those, right, then we know these are all equal. So if we can say that this is equal to 4 times AB, vector AB, and that's going to be equal to the vector AE as such. So that is this right here, this number we have right here, this is what we call our scalar. So that's our scalar multiplication. And then we can go through all these properties, but they all seem pretty self-evident. I'll leave it to you if you want to prove these using geometric means, but we have a commutative property. If we take some scalar, alpha is a scalar, alpha and beta are scalar. If you take alpha times some vector, that's the same as vector times alpha, then we have the associative property with scalar multiplication, where alpha times beta times vector b is the same as alpha times beta times the vector. Then you get the distributive property that works with this. Notice too that we didn't do a distributive property with addition, the vectors that we did before, so you notice that one too. Distributive property as such here too, and then we have the identity property, 1 times the vector is still the vector, and the zero property, 0 times the vector is still going to end up being the zero vector. So there you go. And let's go ahead and look at another problem where we can use some of these scalar identities right here. So this example 5 asks us to, they give us the vectors here, A and vector B, and they want us to be able to, so I'm going to change the pen to something, yeah, that'll be good. Right here, good. And they want us to show twice that alpha, so twice vector A. So vector A here goes over 4 and up 1. So if vector A is 4 up 1, I can go 1, 2, 3, 4. That would be once it, but twice it'd be 1, 2, 3, 4, and up here. So this guy right here would be the vector 2A, right? Good. Now, if I wanted to do negative 3b, now b is over 2 up 3, so it'd be from up 2 over 3. That would be that one, right? But we want to make negative 3, so it's going to go the opposite direction, but it's going to be scaled by 3, right? So it goes here, 1, 2, 3, here. So that's that vector right there. I should point these in this direction so we know this. So this is negative 3b, right? And then the last thing it wants us to do is 2a minus 3b. So for us to do that, I'm going to actually do something like this. And you can see how this works out. So here are my two vectors, right? And then I can take this vector right here and move it over. Let's put this one right here. And let's move. Let's do this, right? Actually, I should just move. Let's move that right there, and let's copy this whole thing. Kind of want to move it and center it right there. Better yet, actually, what I want to do right here, we want to connect it right there. That's what we want to do. So now if we connect these two vectors, now I can go ahead and draw what this vector would look like. This plus this would be this vector right here, and that is the vector negative 3b. Let's write it this way. This vector right here would be 2a minus 3b. It's a proper way, and that's what that vector looks like. Sound good, guys? Thanks.